Let's do it. Let's go. I like a clicker. Okay. Hi, everybody. We're going to start. So this is the Introduction to FRC Programming presentation. I'm Josh Young, and we'll talk a little more about who I am in a second. So just so you guys get to know me a little bit, to like humanize me, I guess. My name is Josh Young once again. I'm a freshman at Northeastern University. I'm a computer science, computer engineering major. I've been on the student on neutrons for the last 3 years, and now I'm a mentor. So, yeah. Okay. So, an overview of what we're gonna cover here. We're gonna start by talking about some of the control system components, sensors. We're gonna talk about the basics of an FRC program and what an iterative versus command-based robot is. We're going to talk a little bit about control theory, and then we're going to talk about some new features that FRC is implementing in 2019. Then we're going to have a little question and answer thing. Okay, so we're going to start with the control system components. I think this is important to know because when you're writing code, you're going to want to know what you're controlling and how you're going to control it and what it's for exactly. So we're going to talk about some of the main components. There's a lot more control system things that are in the FRC robot, but these are the main ones you really have to worry about. So the main thing that you need to really worry about is the RoboRio, right? So this is the brain of the entire robot. It holds and runs all of your code. Yeah. So most things you worry about, all the motors and sensors and stuff, plug directly into it, and it connects to your driver station so you can deploy code and control the robot. It's really important to know how this works at a very deep level because it's your best friend. So I think the most important things on this would be stuff over here. Would be the Ethernet port because when you drop code at competition or whatever, you're just gonna take an Ethernet cord, connect it to your driver station laptop, connect it right into the Ethernet, and do your thing. The digital input and output pins and the PWM pins are important to know because usually things like sensors will go into DIO pins and things like motors will go into the PWM pins. These are labeled with numbers, so these correspond in your code. So you'll set constants to control motors or set constants to read off a sensor that's digital. And this thing right here is a custom electronics port. It's important because usually you'll have something like a gyro or maybe a Spartan board for those who know what that is. Yeah, it just adds a little bit more functionality to what you have. So the FRC driver station and controls are also very important. So what the FRC driver station is a piece of software that runs off basically any Windows computer. It looks like this. So basically, yeah, if you have a computer, you can download this and run it. And it basically allows you to run teleoperated modes, autonomous, practice, and test. No one uses these two. And you can enable and disable. It's also what you use to connect basically controllers to your you connect controllers to this, and that's basically how you control the robot. You should become very acclimated with it because that's how you test things. You can use it to debug with Smart Dashboard or Shuffleboard. That's how you get those things. You can also see some things like communications, robot code, and joysticks. So communications basically means you're talking to the RoboRio, so you can actually deploy and drop code or control the robot. Robot code, that's red, so that means there's no code on this robot. If that's green, that means your code is working and everything's running as it should be. And joysticks are basically any type of control. So usually you'll have joystick Z, a joystick for the driver and a joystick for the operator. There's lots of different controls options that you can use to actually do this. Some people like to use joysticks. Some people like to just use standard Xbox controllers. That's what the Neutrons does. But you can really, if it has buttons and stuff, you can make it work. Okay, the pneumatic control module, or the PCM, is basically what controls basically any pneumatic system. It's pretty simple. It's controlled over CAN. We'll talk more about what CAN is in a little bit. It basically has specified ports for the compressor, pressure switch, and solenoids. These will also be constants in your code. And basically, say you have a solenoid in port 0, you can send a signal over that port to either send air forward or stop sending air. For the compressor, you can turn it on and off. And for the pressure switch, I think you can release air. I don't know why you would ever do that. But yeah, that's that. So there's two types of motor controllers that I know of and that are used typically in FRC. There's CAN and PWM. What CAN and PWM are two different types of like control. As a programmer, you're not really worrying about too much of how those work like crazy, but CAN is control area network bus control. So the way this works is one end, so these two green wires will plug into like the Robo Rio, and they'll daisy chain all the way to the PDM using only those two wires. You don't have to worry about too much of that. It's just a type of motor controller you're using. This is a Talon SRX, which is a type of motor controller. So the reason this is useful is because you can use the CTRE library to help like do like advanced control systems. There's a lot of like baked-in stuff that you can just use right out of the box essentially to like do motion profiling or PID stuff, which we'll talk a little bit more later, not too much though. And the way this works in code is you have unique addresses that are controlled through firmware. So you can like go right into the Rio's like software and like readdress these to match what your code is or vice versa. PWM is pulse width modulation. Each motor controller will plug directly into a PWM port and into power. So you do it over and over again as opposed to just like daisy chaining. Yeah, and the PWM signals are based on where they are in like on the Rio. So like when I was talking about the Robo Rio with the PWM ports, that's how you control those instead of having the addresses controlled through firmware. So these usually only take two inputs. These only take like really one input, -1 or -1 to 1, -1 being full backward and 1 being full forward. And yeah, that's that. So now we're going to talk about sensors. There's a couple of sensors you need to know because like that's how you control the robot. Like you can do cool things with them. Yeah, sensors. So encoders are a feedback device that allows for the tracking of how much an output shaft has turned. It counts in encoder clicks where an n number of clicks equals one full rotation. So something like the CTRE magnetic encoder will be like 4,096 encoder clicks per one revolution. And you can use that number to do like precise control such as distance driving, velocity set points, or like linear motion in an elevator. I have code here, right? Oh, wait, no, I don't. I thought I did. Yeah. So, like, if you knew, like, software. If you knew, like, how, like, the, like, circumference of a wheel and, like, say the circumference of your wheel is, like, 6 inches and you know that you went 4,096 ticks, you know you went forward 6 inches, if that makes any sense. Next are IMUs, which are essentially just your gyros and accelerometers. So gyros are a feedback device that just measures your change in angle, and accelerometers basically just measure your acceleration. So there's 3 types of like angles that you can measure with most gyros. There's roll, which is like this, yaw, which is like this, and then pitch, which is like this. You really only worry about yaw because your robot's not going to be rolling or pitching, hopefully. Hopefully. That happens sometimes. But yeah, us too. Yeah, usually this is mostly used as for turning in place or like, yeah, it's usually just used for turning in place. It helps with like just reorienting yourself and like following a path during like autonomous or something. There's my encoder demo. So yeah, so this is just like, okay, we're just skip this. I don't want to, this is, yeah. There's 3 other types of sensors that are cool that are used a lot. There's IR sensors, which basically like senses if an object is in front of it, and you can tune this to be within a certain range. So like you can have like a dead zone in front and behind it, and like if it's close enough, like it'll turn on, and usually this is either means it's on or off. So like if there's something in front of it or there's not something in front of it. We actually use an IR sensor, this exact IR sensor, this last year in 2018, where like if we took in a cube and the IR sensor got triggered, we would automatically clamp and lift to a certain position. Similarly, our limit switches. So you see that little metal tab. If that metal tab gets pressed down, it'll be like, it knows it's pressed down. So it's either, once again, on or off. Off, it's not pressed down. On, if it is pressed down. And this can be used for something like a hard stop on an elevator. So like if your elevator is going up and you want to stop going up when it gets to a certain point, you can have like a limit switch there, and like it'll stop all control to the elevator once it hits that. And then there's the Hall effect sensor, which we tried to use this year. We kind of scrapped it though, but it just senses whether or not a magnet is within its detection range. So like Once again, on or off if a magnet is near it, on if it's a magnet is near it, off if not. Yeah. So now we're going to start covering the actual basics of an FRC program. So we're going to talk about like the main components of it. We're not going to look at any code. We're just going to talk about like the different main classes that you need to worry about and how they function, how they interact with each other in your program. The first thing you should know is the difference between iterative-based robots and command-based robots. The neutrons use command-based robots, which I'll explain in the next slide. But basically, what an iterative-based robot is an easy state transition between two methods, which are init, which is called once at the beginning of that phase, and then periodic, which will be called indefinitely for each loop of the code. So it's basically like a while loop that runs forever until you tell it to stop running. That allows for parameters and functions to be continuously updated and ran as your robot drives around the field and plays the game. Very similarly is a command-based robot, but the only difference between a command-based robot and an iterative-based robot is the introduction of the concept of commands. So commands are a special type of object that is made for one single action and then deleted. It communicates directly with a subsystem such as an elevator or a drivetrain or an intake or a shooter. Once again, it has an init method that helps set up whatever the execution is. So that's the one-time setup thing. So once you make that command in code, it'll initialize it. And then it'll go into an execute thing, which is also another loop similar to periodic that'll run indefinitely until you hit a certain thing in your end. There's an is finished thing. That's basically like your stop for it. So once that is finished returns true, it'll call end and it'll clean up basically anything that the command made or may have done. So say you had a command that ran an elevator to a set point. Once your elevator was in a certain tolerance of your set point, it'll call end, stop the elevator, and then go on to whatever else you may be doing. There's also an interrupted thing that will kind of save you if something else happens during. So if you're running the elevator and you give it another input, interrupted will be called because the first command got interrupted by the second command. These are very, very useful because they can be used throughout your robot program and communicates with the robot operator interface. So all your commands can be mapped to buttons directly. So say you have lift elevator to switch height on button X, you can press button X and it'll just automatically do it based by calling with that command. So this makes it very useful for integration throughout your code. And also can be called during your autonomous training. So if you have a drive path command, you can call the drive path command and it'll run during auto. It just makes it very modular almost, and you can use all these commands in different places. So we're going to be talking about these 5 things. And I kind of find a better picture to explain this because it's code. But basically we're going to be talking about the robot, the operator interface class, the robot map class, and commands and subsystems. This is something else. That's just things we use math, I guess. So the main thing you need to worry about is the robot class. I think this is the most important class in your entire program because it's what controls and runs the robot and controls the flow of what happens by tying everything together. So it contains an init and loop function for teleop, autonomous, disabled, and test. And I've never used test in my 3 years of programming. I don't know if anyone has ever used test. See, some people use test. Mm-hmm. Okay, so yeah, there's some usages for it. I haven't explored it much, but there's some stuff. So once again, the init and loop function are that one-time setup and periodically called loop that runs indefinitely until you tell it not to. So there's now subsystem classes. So typically, you'll have a subsystem class for each subsystem of your robot. So for example, you'll have a subsystem class for your elevator, a subsystem class for your drivetrain, a subsystem class for your intake, and so on and so forth. So these things will have different actuators and sensors of the class. So you'll have your motor controllers, your different IR sensors, encoders, et cetera, et cetera. You should have functions that interact and control parts of the subsystem. So you'll have something like run elevator up, run elevator down, run elevator to position. You'll also have a default command that runs when no other commands are running. So something just analog control off a joystick would be something. And these subsystem classes will be created as objects in robot. So you'll have like at the top in your robot class, like at the top of this one, all your different subsystems listed out as like drivetrain, elevator, intake, and all your other ones. So an elevator, for example, could have motor controllers and their encoders, functions that control the elevator directly and move to different set points, and a default command that could be direct control using a joystick. Yes? They'll be posted on our website and the Compass Alliance probably, www.neutrons.com. All the other presentations will also be posted online at some point, probably later tonight. No problem. The other three are a little more simpler. They're the operator. So the first one is the operator interface, also just named OI class. So basically that just maps like all your different buttons to your different commands. Not sure how it works in iterative-based robots, but I know for command-based, which the Neutrons use, like button 1 could be like run to intake position, button X could be run to switch, button Y could be run to scale. And like you could just map all these buttons to different commands, and as soon as you press those buttons, it'll do the thing. The robot map class is a running list of all your constants on your robot. So you can have things like your wheelbase width, or like all the different IDs for your CAN devices or PWM devices. So basically this makes it so like you're not like hard coding numbers when you're like controlling something. It's just something that you can change in one place and it changes across your entire code base. And the commands is a folder that separates and organizes all your commands of your robot. So basically what you usually do is you'll have commands for all your different subsystems. So like the elevators are cube lift, the drivetrain, intake, and you'll have a bunch of different stuff that just holds all your commands. That makes sense. Now we're going to go into control theory. I'm going to ramp it up a little bit. This is mostly used for like, you can do advanced control because for most things, you're not going to use like straight like input. You're going to have something like a PID loop or some type of controller so you can like reach a set point. It's going to be fun. Okay. So an introduction to control theory is it's basically making a physical system do what you want. You use sensors and actuators to get to a specific goal that you set, and you can apply a loop to that goal and have error and stuff. So a system is a physical system with actuators and sensors, and these systems will have an internal state. And these states are the variables that describe a system's operations. So something like a drivetrain would have your position, your velocity, your output voltage, etc. A sensor is a device that's used to measure the state of a system. These are the same things that we covered earlier, such as the encoder, gyro, whatever sensors you may use that can describe this system. And then your actuator is the actual device that is used to affect the state of the system. So it's something like a motor or a servo. So a very simple controller that is kind of like used to like start off is called a bang-bang controller. So you start with the goal position. In this case, it's that red line at around 37. And you start at like 0. So if you're like, so the way this works is if you're below the error, like you need to get there, you go full power forward. If you're past the error, you go full power backward. So you're kind of just oscillating at your set point, and that's why you see the very sharp things. This can put a lot of stress on certain systems, such as an elevator or a drivetrain, but if you're talking about something like a shooter that like barely adjusts, it can be effectively controlled using a bang-bang controller. But what we really want to do is calculus. So derivatives. So yeah, who here hasn't taken calculus? Okay, a fair amount of you, probably a good amount of you. So we're just going to do a very quick crash course on what a derivative is. So say this is a position versus time graph. At any point, like that green line on the graph is your velocity because that's your average rate of change that's very close. We call it the instantaneous rate of change. So it's basically how fast something is changing. And basically with a position versus time graph, which we can map out in our code, we can get the velocity at any point in our system. And we can also find the acceleration from this velocity. Integrals. So integrals are the area under your curve. So once again, if this is a position versus time graph, the area under your curve will be the amount of distance you traveled or your displacement. Yeah. So this comes in use when you're talking about PID loops. So So PID loops is so the way PID works is you're always at any point in your system as you're trying to reach a set point, you're going to have an error. Your error is going to be your goal minus your current position. So if my goal is 10 and my position is 3, my error is going to be 7. So based off this error, you're going to have 3 different terms that work along with this error. So your proportional gain, so PID loop, is based off that error. So your error is 7, you're going to have a term that's proportional to that number of 7 that'll make you move forward. Yeah. Your integral term, the I in the PID, is how much steady state error that you've been accumulating over time. So this comes in useful when like you're right into the line, but your proportional and derivative gain aren't enough to like really push you there. Your steady state error will build because your displacement it just keeps building and building over and over. And eventually you'll get enough power to just push you over, if that makes sense. And then your derivative will help you like slow down when your robot's moving too fast. So when we're talking about derivatives, you can get your velocity at any point. If your velocity is too big, it'll multiply by your derivative gain and slow you down. So this works. So most things can be controlled by a PD loop. Some people use integral for some things, such as like driving a path, so you can like overcome the friction of the carpet. But usually that's something you really don't have to worry about in most systems. So you have a proportional gain to like get you going, and as you approach your goal, the derivative gain will slow you down. On the graph, a PD loop can be represented by the green line. So you're going to go really fast. You're probably going to overshoot a little bit, but as soon as you overshoot, you're going to slow down and just level out at your goal, which is the blue line. Okay. So this is what a PID function looks like. This is kind of weird to look at. So like once again, your gain times your error plus your gain I times your integral term plus your gain minus your D gain minus your derivative. This is a better slide to explain it. Yeah, so using an elevator, for example, your goal is to move to a specific position. Your output will be between -12 volts and 12 volts. So you should think of your gains in terms of units, where your E is your U is your output in volts, and your error is E in meters. So your gain P will be in what units? So knowing your units makes guessing much more reasonable. PID is something you just need to kind of work with, and that's kind of hard to explain. Once you start working with it, it starts to make a lot of sense. I know I'm probably not the best at explaining it right now, but as you practice and learn and start using these kind of things, it'll make a lot more sense. So you can tune PID by increasing your P term until your system starts to oscillate. If the system starts to oscillate, you're going to move down a little bit, and then you're going to start adding some KD to help it level out. And then if there's a steady state error because of like a carpet or something, you'll add an I term so you can overcome that steady state error. So yeah, so you're increasing KP until it begins to oscillate. You can see, and then you'll keep going. Yeah. So now we're going to talk about some new stuff for FRC in 2019. So first is adding a lot of cool stuff to WPI lib, which yeah, so we're going to talk about some of that stuff. So opposed for the last 3 years, their first and FRC teams are going to be using Visual Studio Code opposed to Eclipse. So there's a lot about this online. It's just basically like replacing Eclipse, and all the WPI lib extension stuff is now going to be on Visual Studio, which you basically just download Visual Studio. You go to install new software, and you can just type WPI lib in the command palette, and it'll basically download the stuff onto there. And it works essentially the same as Eclipse. There's also other new features. If you go to Screen Steps Live, you can see a lot more of this. There's going to be a reference page at the end of this that kind of explains some of this. Yeah. That's just something cool that's new. I think it's really cool that they're moving away from Eclipse, because I personally didn't like Eclipse at all. There's a lot of new Shuffleboard features this year, and for those that are not acclimated with Shuffleboard, it's what replaced Smart Dashboard last year. So Shuffleboard is just a dashboard based for FRC that uses newer technology such as Java FX that makes it look a lot nicer compared to the old Smart Dashboard. So you can have like this blue color and cool like gyro things and a bunch of stuff that right here that this kind of describes what's going on in your code. And it's just a lot of new stuff. There's a lot of new Shuffleboard features that they're adding. They can also use on Screen Steps Live that kind of explain what's going on. They fundamentally work the same way, but Shuffleboard has many features that aren't in Smart Dashboard. And the last thing we're going to cover is Pathfinder and Pathfinder. Yeah, Mm-hmm.
Did you use it?
No, we didn't use it.
So I just, it was new last year. We had some experience with Smart Dashboard, but we didn't really have the Smart Dashboard. We just just all looked at it. We were scared.
Mm-hmm.
Said no.
So
I'm just curious if people had experience with it, and if it was a little more stable and a better choice.
So we were trying to use it last year, but it actually gave us a lot of problems. So we just went back to what we knew because we just want to have something that works. Which was Smart Dashboard. So we used Smart Dashboard this year. I know I've heard that they fixed a lot of those issues that Shuffleboard has, and I could see over as the build season progressed that Shuffleboard was getting continuous updates that made it more and more better. But we just stuck with Smart Dashboards because what we knew, and it worked out for us. We're gonna try to use Shuffleboard this year though. So the main difference between Shuffleboard and Smart Dashboard is, in code, everything's exactly the same, but Shuffleboard looks a lot nicer. I could show you FRC Smart Dashboard. It just looks very, very plain. It's just plain text boxes and very, very, very basic things. But this has
there's also stuff where you can drag out everything.
Yeah, everything's overlaid on top of each other. Shuffleboard has this cool grid system, and you can save the configurations, and it just looks a lot nicer. It's a lot more user friendly. That's the main difference. Cool. So the last thing that we're going to cover is Pathfinder and Pathfinder 2. So Pathfinder is actually this really neat GUI that allows you to plan motion profiles from a starting point to an endpoint and link them together using autonomous things. And it allows for quick and clean generation of motion profiles that can be used with Pathfinder 2, which is basically the official implementation of Jackie's Pathfinder, which was a library that could be used that the neutrons actually used last year for generating and following motion profiles. So these two can be used in conjunction for very smooth driving and repeatable autonomous routines. So that's all the content. Oh, there's one more thing. Sorry. So we discussed a lot here today, probably a little fast and probably not too in depth. I watch a lot of presentations online, and they really just help I feel like presentations kind of tell you what you need to know, not how you know it. So I feel the best way to learn all of this stuff is kind of just know that's been said and kind of go and explore on your own and practice it on your own and get a mastery of it on your own time. So there's a lot of good resources out there, such as Chief Delphi, the Compass Alliance, and Screen Steps Live. So Chief Delphi is essentially a big forum, a bunch of people talking about FRC and things to know about FRC. The Compass Alliance is actually this big thing that we're having a presentation on, and it basically is 10 teams from across, I think 10 teams, or maybe a little more than 10 teams from across the world that are collaborating on a big resource depot for first teams to learn. So if you just look up FRC, the Compass Alliance, it's this website with a ton of resources. That's also very cool. You should check that out. And then there's the Screen Steps Live, which is basically official first documentation of the first control system. That's where I pulled most of this stuff from today. So these are definitely 3 resources that you should definitely utilize. There's also a ton more out there. Whatever you find, use it. Use the internet. It helps. That's everything I have. I guess we can now go into a question and answer phase if anyone has any questions. Yes?
So we're talking about the new 2019 stuff. One of the things is everything is right over here. And so I'm a little confused about whether or not we have to use VS Code. I know VS Code is a game that's heard before, but we haven't been to the test of it.
I don't think you have to.
So
it's what they're supporting, right? So you were never actually tied to Eclipse, especially with things like Rio. You can just build your command line. But I think what this means is just if you're at a competition, need help with something, they'll know how to support VS Code, right? So I don't think you're really bound to it.
So being on the neutrons for the last 3 years, I don't think we used Eclipse once. We always use IntelliJ. It's just what first decides to officially support and make really easy to use for newer teams and just So yeah, you can probably still use Eclipse, and it'll probably still work fine. There's just gonna be a couple more like you might run into a couple more issues that you can't find online as easy, but I'm sure it'll still be very usable. Yes.
Getting started out, and I use LJ or and I technically
From a Mac. So the only thing you can't do from a Mac is you can't use the driver station, which can be a little annoying at sometimes because like you'll drop code from your laptop and you'll have to use like another driver station laptop to like control the robot. But literally like everything you can do except for controlling the robot can be done from a Mac. If you want to be able to control the robot from the Mac, you could also just like use Boot Camp or something. That's always an option.
We can confirm that we had a number of students on our team that were Mac based. They were as productive writing code.
very excited on our team there.
Yeah, that's probably frightening. I mean, we had a couple of team laptops that we used for actually driving and controlling the robot, and so the pattern that we tended to follow was, either if there were just a couple people that were around, someone might drop code from Mac and then just drive immediately. More likely, we actually had a number of a relatively large number of software doing slightly different things at the same time. And we just pushed up together and downloaded it on the Team Robot.
Yes.
Our team's using the robot builder.
I haven't worked with it at all, to be completely honest with you. I've heard a lot about it, and I've heard a lot of teams had a lot of success with it. Going back to like the resources thing, there's a lot. I know on like Screen Steps Live, there's a ton of support for that and a ton of documentation on how to get that working and running. I personally don't have a ton of experience with that, unfortunately.
Is that the LabVIEW center?
It's this kind of like practical, not really. Like it's hoping for how to scale it to your code.
So like with the robot builder, isn't it the thing where like you can like drag all your motors and like all the different subsystems you have, and then like it'll auto generate like just like a skeleton code, and then you can start filling it in with like your own custom controlling. Yeah, I think it's probably definitely a useful tool. Yeah. Yes.
The teams used to drive straight. Gyro.
So
Motors.
teams will usually use a mix of both gyro and encoder. So the gyros come in useful. So I know we went through PID loops pretty fast, but you'll run a PID loop on a gyro where like your goal will be 0. You'll start at 0, and as you drive forward, you may like drift 5 degrees or drift 5 degrees in one way, and the PID will automatically like basically readjust you and like keep you on that path. So we use gyro.
In the context of telling them.
Well, I guess my follow-up is
So they use both.
So almost every single team will use some sort of gyro feedback in their code, because if you don't, you'll just drift off, and if you don't use encoders, you'll like won't drive the same amount every time. So sensors become a very, very important part for repeatability of your autonomous routines. For a teleup, they're not used as much, but you can use them. So like I can speak in 2017, we had our driver have a button that will basically like hold. So like our driver would like basically just like drive across the field really fast without like just like gun it down the field, so like get to like one of the positions. So he would hold down like a button that would hold him at his current angle, and then he was like drive forward, and that would basically make it so he didn't have to like adjust left or right, and that's where that can become useful. Yeah. Yes.
What if the addition
Having the field.
thinking that nation is part of your whole system? We need simulation.
Is that the Linux based one, or is it going to be something new?
That's in every virtual field. It has a data set.
I actually haven't heard of that.
It's like giving you a perfect map.
Mhm.
I think it was I have all of the fields that we yeah, is that I need to hear.
Is it gonna be like a 3D rendering of the field and like?
I have no idea about the details of it.
Yeah, because I haven't heard anything about that. Oh, so you can do simulation in it too.
I'm skeptical. I'm skeptical. And we had the luxury of actually having a full field last year. There was
It's
no
not
way
simulation.
that I could imagine anybody.
There's a
actually
Linux
being able to
simulation tool.
replicate that value. I mean,
Something like
I
that.
think, we had a decent map of the field that we kind of, I guess, at the beginning of the season, we tried to use to say, oh, there's options here, where am I? Eventually, that just went away, right? The amount of time it took to try to keep that in sync with reality was not worth the extra value that we got from it. I would love it if we could actually have something that could truly simulate even basic, bedrock position or anything like that. I'm a little skeptical. I love it, right? If it actually looks like it's got some value, like not counting.
Yeah.
There actually is a program for that. It's called VXT Synthesis. It's a virtual field and you're able to import your robot. The only issue with it though is it's an Inventor importer, not a SolidWorks importer.
Is this the Linux? So I've seen this simulation
Yeah.
a couple times, and I've never, it always feels like people are sort of flirting with it, but not kind of relying on it.
So
It's a fun program to use that have all your joints, strengths, coordinates correct. I've tried to use it. It's very difficult, but they're improving it every year. They actually use first alumni to make the program.
And it's doing mechanical simulations, or it's doing
It can do
sort of all of the above.
It can do all of them. You're even able to put your autonomous code into the program, run your code, and see how it looks.
And they have like simulation modules for the different encoders or some stack of them.
Yeah. Okay.
So the thing, my opinion on simulations will always be that they're really useful for proof of concept and like it'll show maybe if something will work, but you really will never know unless you try it on a real robot. Nothing beats reality. Yes.
We don't have the luxury of having, and frankly, most of them doing back to the bot the day before comp. At least so, how do you think this is going about doing some of that autonomous stuff without? I know it's really you're trying a lot of things and really wasting a lot of time trying to auto still not ready.
So the neutrons really didn't have access to the practice field until like this year, and it was very limited access to a practice field. So what we would do is we would try to find literally any classroom with like carpet, and we would tape out like very small sections of the field, and that's how we would do it.
The practice spot with the
So this year we actually just made our mechanical team made a second drivetrain, and that's when we started testing things. But before that, yeah, we would just like tape out. We would wait until we got the robot, taped it out, and then would like go at it. You could if you have like older robots that are like just kind of like chilling in a corner somewhere. I'm not sure if you guys like take them apart after every year. You could also yeah. So that can be useful to like just like getting like code that like just like having like a ready amount of code for that, and then like tuning for when you get the real robot.
A lot of times, like going through the motions of tuning, like getting all your auto driving right on the practice spot, makes it a lot easier once you get it to the real bot. Like even if it's just the drive phase, right? If you spend all that time figuring out your motion profiles and which way all the signs go and stuff, it'll be a lot easier once you transfer the real robot.
Mm-hmm. Yes.
So, we're a rookie team. How do you know when you get
Welcome. We've all been working teams. Thank you.
how do you know when you get to the competition? People set up the field management system to trigger.
Okay, yeah. So going back to the driver's, I'll go back in a second. So yeah, going back to the driver's station, all the way back. We're getting there. So the driver's station is actually really cool because as soon as you plug into the field management system, like as soon as you plug into the field, so like when you go to play your first match, you'll placed on your driver's station laptop, and
But also when you like tether up outside the field.
so when you tether up to
like in your lap or something.
yeah, so when you tether up, so when you tether up to your robot like at home, essentially, this is this is what you'll see. You have complete control over everything. You can turn on and turn off teleop, turn off and turn on autonomous, and these two other ones
that works. I get that part. That works. You just trust that when it gets to the competition, it's gonna work.
Yeah, so as soon as you plug in the field management system, this kind of just all goes away and it says FMS connected, and then the field manages everything from turning on, turning off teleop, and turning on and turning on autonomous.
So I think in general, this actually works far better than I ever expected. And when you get to the field, and if there's a problem with the field, they help figure out what's going on. Nobody just presumes that their stuff is perfect and your stuff must be broken. Right? They will come up, they'll hold the match to make sure things are set up and things like that. And there's practice time and so on. If things are working in your lab, there's a really good chance.
So this is as far as you go.
That's
the driver's station. You don't have to set up the system.
that's
Yeah, the FMS handles all that for you.
This last year, we had an issue where it was physically impossible for us to test it until we connected to the field. Actually, with in the driver's field beds, input for autos. So we had in the driver's station our autos for like the left and right push scale positions. I was seeing it at all. Left and right push scale position already in there. But we were calling for them in whether robot initiated instead of when autonomous initiated. So we were calling for values that didn't exist when the robot was first connected. They didn't exist for auto. So like it worked fine when we were at home, but as soon as we connected to the field, work. We had to figure that out. So it's that accuracy, like it's really important you can try and get. They normally have like night for comp and a test session. It crashes running.
Yeah, the same thing happened to us actually, and we just had to move some stuff around and do it after autonomous started.
Yes, we did.
Yeah, sure. That's why. So like at the beginning of every competition, you'll have like 2, 3, 4 practice matches, and those will basically allow you to like work out some of the first issues that you may have, and those become really helpful, such as when for some reason you don't know why your code's not running because you don't have things that the field's not giving you yet. Does anyone have any other questions?
Last one.
Yes.
What are people using for sort of code management? 5 people working on the same code.
So like what the neutrons use is this like GitHub. I can just show you to be honest with you. I don't know GitHub. I don't know the URL. I don't want to find it. So like we use GitHub. There's a lot of resources on how this works online. So basically like it just allows you to make branches for all your different things. So we have branches for all of our different competitions, all the different weeks, all the different features that we added. We don't use it the most efficiently, to be honest. So like what you're supposed to do is like you'll make a new branch for like a new feature. So like you can make a new branch for adding drivetrain, a new branch for adding an elevator, and this just allows for like multiple people work on it at once and all being in the same place, and like this allows for like it's just basically we use this.
Basically, when you have 2 different code bases, 2 different branches, but they're both based off of the same like master branch. You're going to want to eventually merge them together, and GitHub allows you to do that really easily. And it automatically resolves any conflicts that may be between the 2 code bases. It's used by a lot of professional companies.
Yeah, all of the IDEs integrate really nicely with Git, and there's a command line version of Git. There's also Atlassian has a project called Source Tree. The UI is almost everything. So students of Git figure out it actually works pretty easily. Source Tree. It's by the same company that makes Jira and
Yes. Mhm.
So I know there is some stuff in like first has some. I know you can has some stuff
Mhm.
like PID, but like I've noticed by doing our calculations, you just gave a lot of time. How do you kind of set it up and deal with that? I guess like.
So we did both. So we used a lot of CTRE stuff this year for our elevator, which is the Talon SRX and Crossroad Electronics. It's a brand that makes motor controllers. They have a library that makes it very, very easy for that. You just give it constants and tell it to go to position, and it kind of just does it. For things that we do on our own, we have a PID controller class. If you remember when I talked about this, I was like ignore this, and there would be like our PID controller class, and we'll make a PID controller, and that's where we'll feed it our gains, and it'll give us our input and output. So the reason I didn't go in too much depth about PID is because after lunch there's going to be a 3-hour presentation on motion profiling and motion control, and a guy from 195 is going to talk a lot about that, a lot more in depth than that. So if you're interested in that kind of stuff, I would definitely go with that. Other questions? Okay. So I'm gonna write my information and the team's information right here. If you guys ever have any questions, this is really big. Oh yeah. So this is my personal email, and this one is our team's personal email. So if you ever have any questions or need any help with any of this stuff, rookie team, definitely feel free to reach out. We love to help, and we definitely want to do that. So yes, of course.
Nice.
Yeah. Trunks.com.
15 minutes. 15 minutes.
Nice.
I didn't do that bad.
Vision slide.
Huh? Vision slide? Vision slide.
Snap.
Vision slide. Oh my god. That was great.
Stop it.